Okay, we're recording again, I think. Yep. Thank you, Roman. I appreciate. Thank you all for being understanding. Okay, so y'all can see my screen again, and then see back to mirroring. So y'all can see my iPad once again. Okay,
Yeah, we can
so
see everything.
cool, cool. So the Euler Tour essentially is this idea that if you've got a node, you can draw these little dots around that node. And this dot is your pre-order traversal dot. This is your in-order traversal dot, and then this is your post-order traversal dot. And essentially, if you do this to every node, then you can compute the post-order, pre-order, in-order traversal by connecting whichever dot makes sense for that type of traversal, right? So if we're doing pre-order, let's see. Yeah, so if we're doing pre-order traversal, then we're looking at these left dots here. And starting from the first of the left dots, we just connect these, and we get our output as A, B, D, E, C, and this is pre-order. If we do the middle dots, we're going to get in order, which I don't think you should ever think about doing middle dots because in order is just so simple. But nonetheless, it'll give you the correct output, which in this case is going to be what? D, B, E, A, C. So this is in order. And then if you do the right dots, that should get you your post-order traversal, which in this case is this. So that's what B, E, B, C, A. And like I said last time, notice this weird property that the root node will be the last one that you print. Confirm that this is correct. That's your Euler Tour. That's your traversal. Okay, so we've talked enough about tree traversal, I think. Let's get into tree balancing. So I think Roman, you asked for tree balancing, so sorry to have kept you waiting so long. This is a huge concept for the exam. Part of the reason I wanted to make this review longer than normal is that, this is like all of the stuff that y'all would have seen on the slides. Uh, wow, we've gone through a lot so far. Tree balancing is kind of like something that you're expected to know, expected to be able to do, and it's the type of concept that you're not gonna get anything by staring at a textbook, I don't think. So, let's do some examples by hand. So the first type of tree balancing that we need to know is AVL balancing. So the motivation behind this is when you've got a tree, it could look like it could look like this, right? It looks nice and relatively balanced, right? We can say that the height is relatively log n. But you could also have a tree that looks like this. And what do you do about that, right? Because now this is kind of like it's kind of like a linked list, but it's like at this point, why would you even make a tree? Like you're using all of this extra space. You could have just made a linked list. So if you're going to say I am making a tree, then you need to be better than a linked list, because if you needed the functionality of a linked list, it would take up less space because you wouldn't have this, unused pointer or whatever it is. So if you're making a tree, you need to make sure that it's balanced. And as I said before, roughly if you've got a tree that looks something like this, you can just kind of intuitively see that it's balanced. And then if you have a tree that looks something like this, you can kind of intuitively see that it's not balanced. And we can actually formalize this concept with a definition of balance factors. So the idea behind AVL is, and I'm going to switch to red right here. We can define balance to be height of left minus height of right. Or in a more mathematical notation, we can say balance is equal to height of left minus height of right. And also we can say that a tree is a valid AVL. So a valid AVL tree has balance included in this set for all nodes. So let's give an example. So for a tree that I decided was bad, so let's imagine you've got this not optimal tree right here. You can intuitively see that this is bad, right? This is not what we're going for. This is more similar to the linked list, and therefore it needs to be addressed. You can intuitively kind of tell it's unbalanced, but because we just came up with a formal definition up here, let's actually let's actually apply that formal definition. So as we're looking at each node, we're going to compute the balance factor. So for 3, balance factor is equal to height of left minus height of right, which in this case is going to be 0 minus 0. So it's going to have a balance factor of 0. And this will be the case for any leaf node, right? Because, it's going to have no children, so therefore it'll always just be balanced. So we can go ahead and put that there. For 4, we're looking at balance is equal to height of the left minus height of the right, which in this case is going to be what? 1 minus 0, so 1. For 8, we are again looking at height of left minus the height of the right, which in this case is going to be 2 minus 1, so that's 1. So if you were given this little subset of the tree and you were asked, is this a valid AVL tree? The answer is yes, because for each node, it's got a balance factor between -1 and 1 inclusive. For 2, we're looking at height of left minus height of right, and that's going to be 0 minus 3, I think. Yeah, 1, 2, 3. So we can say that this is -3, and this is no longer a valid AVL tree. See, this will be -4, and then for 9, we're going to have height of left minus height of right, which the left tree is going to have 5 nodes, and the right tree is going to have 0 nodes. So as you can see, when we're looking at what I said, oh, this is intuitively like not a great tree, we can formalize that and we see, yeah, this was not a great tree. We end up getting these crazy coefficients. So AVL offers a solution to this problem, which is whenever you get the imbalanced tree, you rotate that tree such that it is balanced. And the rotations happen on every insert, and the tree is balanced after every insert. So if you're looking at, imagine you've got 3 nodes. So we've got these nodes. Let's say we've got 1, 2, and 3. If you're looking at these 3 nodes and you're constructing a tree out of them, there are 5 possible trees that you can make using these 3 nodes, obeying binary search tree rules. So you could either have this, which, as we can see, the balance factor here is going to be 0, or you could have 4 unbalanced trees. So you might have this, you might have this, you might have this, and you might have this. And so the balance factors on all of these trees, as you can see, the leaves will always be 0. So we know that right off the rip. We can see this is going to give us an imbalance. This is going to give us an imbalance. This is going to give us an imbalance. And this is going to give us an imbalance. So all 4 of these trees are not valid AVL trees because they have a node with a balance factor that is not included in this range right here that we drew before. And so the idea behind AVL is that, okay, well, if we get any of these 4 cases, we just convert them back to this case, and then everything is good and everything is balanced. So as we can see, to fix this first case here, we're going to fix this by bringing this node down such that we now have the balanced structure. In this case, we're going to bring the 3 node down such that we have a balanced structure. And as you can see, the balance factor on both of these trees is going to be once again balanced, and we're all good. So this we call our single left. So this is our single left because we did one rotation and it was on the left. And then this is going to be our single right because we did one rotation and it was to the right. And now for these two cases, the first thing we're going to do for these two is we're going to swap these two nodes. You can see the difference here. You're kind of looking at like a line pattern for these, whereas you're kind of looking at a triangle pattern for these trees. And if you see the triangle pattern tree, essentially your goal is to take the triangle pattern, turn it into a line pattern, and then turn the line pattern into the balance. So you have two steps in order to get back to balance. So the first step that you're going to do is you're going to swap from the triangle pattern to the line pattern. So in this case, it will be this. You accomplish this by swapping these two nodes. And then we already know how to solve this case because we did that here, right? So this is just going to become 2, 1, 3. And then likewise here, we're going to swap these two nodes from the triangle case to the line case. And we know how to handle this because we already defined it. Okay, and as you can see, the balance factors here are all going to be balanced as well. We call this one, this third one here, we call this the double left. We call this right one here, we call this the double right. And that's based on the direction of the second rotation, the final rotation. So first you do your swap. And then if you do a left rotation as the final one, it's a double left. And if you do a right rotation as the final one, it's a double right. So that's just semantics. And as you can see, something cool happens here because we said this was the pattern that we were looking for. Our single left converged upon that pattern, our single right converged upon that pattern, our double left converged upon that pattern, and our double right converged upon that pattern. You can see each of our cases end up giving us the exact same balanced output. So depending on which of these 4 cases that we see when we insert, we're going to rotate and adjust accordingly. So let's do an example. So imagine we've got some nodes, and let's just say they look like this. If you were building a balanced, well, not balanced, but if you were building a binary search tree like PA4 style, the approach that you would take here is you would just kind of randomly insert these nodes. Well, I say randomly, but you would insert them one at a time, and the shape of the tree is more or less random based on how good is the order of your input, right? So PA4 style, we're doing this. So we just search to find the position where we insert, and then once we've done that, we do our insert. So PA4 style is going to give us an output that looks something like this. And as you can see, this is not so bad. This is not terrible, at least not yet. Yes, this is not awful. This is not the worst, but this, oh, oops, I'm so sorry, y'all. 6 would be, where are my manners? 6 is here. Yeah, so this is not awful. This is not so bad. But now imagine you were given an adversarial input. So you were given an input that's like this. What? Okay, imagine you were given, oops, I'm so sorry, y'all. Okay, so imagine you're given something like this. So PA4 style is going to look like this. 9, 8, 1, 7, 6, 2. Wow, this is terrible. This is really, really awful. 5, 0. And as you can see, if we were to just attempt to calculate the balance factor here, we're all messed up, right? So we've got 0, -1, -2, 3, 4, 0, -4, what, 1, 2, 3, 4, 5, 6, and 7. And as you can see, we're getting these crazy balance factors on this tree. And we said it was only balanced if the balance factor is in this range. So clearly this is not a valid AVL tree. In fact, the tree becomes no longer a valid AVL tree when we get to this case. And remember, this looked familiar. This was one of the edge cases that we defined up here. We know how to handle this. So instead of doing this PA4 style where we just kind of insert with no heed to whether it's balanced or not, let's actually do our AVL rotations upon insert. So we insert 9, insert 8. These are both good. So you can see the balance factor here is, this is still reasonable. It's between -1 and 1. Once we insert 1 here, we're going to have to recompute these balance factors because this does change things. So this is going to give us this, which is going to have these balance factors. And as you can see, we've reached something. This is no longer a valid AVL tree. So to fix this, we're going to do our rotation like we did before. We're going to bring that down. This is going to be a single right rotation. And as you can see, we have now reached a balanced tree again. So let's keep going. Let's add, let's add 7. 7 is added here, and then we're going to have to recompute these balance factors, which will be this. As you can see, this is still a valid AVL tree. So on the test, if you see something that's like this and it says, is this a valid AVL tree? The answer is yes, because the balance for each node is still within our bounds. And now let's add 6, and 6 is going to be here, I believe. Yes, 6 is going to be here. So now we have to update these balances that we had before. So 6 is going to have a balance factor of 0, 1, 2, and 2. And as you can see right away, this little subsection of the tree causes an issue. So we now need to rebalance this. So this is this 176 is the same case as 132, as you can see up here. We're going to fix this with a double left rotation. So let's rewrite what I just drew in this blue circle here. Let's rewrite this over here. So we got 1, 7, and 6. We're going to first swap 6 and 7. So we're going from the triangle case to the line case. And then we're going to do a single left rotation on this case, which will give us this. And we're going to plug this back in to what we had here in the blue tree. So let me rewrite this down here lower. So we had 8 and 9, and then some blue mess, which we decided was going to be 6, 1, 7. So 6, 1, 7. And as you can see, we have now correctly balanced the tree. So where are we? 0, 0, 0, 0, 1. Okay, so balance is restored. What's next? 6. Let's add 2. So 2 is going to be, oops, so sorry. 2 is going to be here. So now we need to update all of our balance factors again, because we just messed them up. So 2 is going to be inserted with the balance factor of 0, and we got -1, 1, and 2. Yes. So once again, we've reached an issue because of this node right here having a value that is not between -1 and 1. And so the reason I draw this blue circle is because as these trees start to get more and more complicated, it's going to be less and less and less obvious how you actually perform the rotation, which nodes in question need to be rotated, and then how you put that rotated structure back into the original structure. So that is really the challenge here. So I'm gonna stay consistent with my colors. You know that, so the first node that is imbalanced is going to be part of your AVL correction. And I think I had a question in a previous Sunday review. Like you drew the tree like, I mean, you drew the AVL structure like this. Why didn't you draw the blue circle around 7, right? You could have just as easily drew the circle like this, right? So how do you know which nodes it is to be balanced? Well, this is mostly the question. And the answer to that is you look where the problem is coming from, right? So the problem is not coming from this path right here where 7 is, right? Because if we were just looking at 8, 6, 9, 7, this is fine, right? This is still a balanced tree. This is fine. The problem came from this path where we have this node. And because this left path is the one that causes the problem, the left path has to be included in the rotation. So hopefully that kind of makes sense. So let's redraw this down here and solve this. We've got 8, 6, 1. We're going to solve this with a single right rotation. So that's going to give us this. And we're going to plug this back into our tree. So it looks like the blue structure was the root, actually. So we've got the blue structure, which is this. And so now what we're going to do is we're going to add back all of the children of 1. So 1 had one child, which is 2. We're going to add back all of the children of 8, which, so let's do that in a second. Let's add the children of 6, which is going to be just this. And then the children of 8 was 9. So the point that I'm really trying to nail down is that when you do your rotation and you decide this is the problem area, this is the solution, this solution will appear in the tree verbatim, right? So when you take this case and you turn it into this case down here, that case, these 3 nodes will be adjacent in this order verbatim in the solution. And that's definitely a place you could get tripped up quite easily. And then now if we recompute the balance factor, it looks like we are good to go again. Balanced AVL tree. So what did we just insert? We inserted 2. Let's insert, I think 4 is next. Yeah, let's insert 4. So 4 is going to go, 4 is going to go here. And now we've got to reset all of these balance factors. So 4 is going to have a balance factor of 0, -1, -2. Right away, we find a problem, and then this is going to be, I think 6 is still balanced. Yeah, 6 is still balanced. Okay, anyways, but right away, see we've got a problem. So let's redraw this blue group as we got 1, 2, 4. We're going to fix this with a single left rotation. And we're going to plug this solution back into the tree verbatim. So the tree that we had was 6, 8, 7, and 9, and then whatever this blue rearrangement was going to be. And verbatim, that is 2, 1, 4. And as you can see, this is beautiful. When we have a full tree, a perfect tree, the balance is perfect. So this is what you want to see. This is great. Now where were we? So we inserted 4. Let's insert 5, see what happens. Okay, so 5 is going to be inserted here. I don't know that this causes a problem, so let's check and make sure it doesn't. So 5 is going to have a balance factor of 0, balance factor of -1, balance factor of -1 again, and then balance factor of 1. Okay, so this structure is less balanced, but it's still good. And then I think our last one to insert was 0. So let's see what happens when we insert 0. And yeah, this will also be fine. Okay, 0. And let's just recompute these balances just to be completely sure. Sleep well at night. We've got 0, 1, 0, 1. Okay, and as you can see, for all nodes, their balance factor is included in the set of, let's say that for all nodes, their balance is included in this set. Therefore, we're good. We're good to go. So, is everyone comfortable with AVL trees now? We've got these base cases, essentially 4 possible cases in which an insert can give you a problem. Like if you imagine this to be like above the line, this was your existing tree. Here, 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 and here. There are 4 ways that you can add a node such that you have caused a problem. And it's why we drew these things out, because we defined the 4 ways in which you fix this. each of those four ways is going to converge upon the correct solution, which, as we can see, in this case, will always lead to balance. And then we just make sure that we rebalance the tree every time we do an insert, and we end up with a tree that is completely balanced, which is here. So I didn't lose anybody, right?
What's the pivot point?
The pivot point. The pivot point. Do you mean like how do you choose like how to pivot here?
Just like I know how to do like the rotations, but just
Yes.
like which one is the pivot point? Is it the one that you're like the parent of the one that you're rotating around, or
Like how do you choose which nodes to rotate?
not necessarily that. Like when you go from 1, 2, 4, that's all on the right, and then do a single left to
Yes.
1, 2, 4. Is
Yes.
2 the pivot point?
Yes, yes, it is. Yeah.
It is. Okay.
Yeah. So
All right.
if you had like nodes 1, 2, and 4, you could write these. The only way that you can write these in a balanced way is like this. If you try to write these nodes in any other order, uh, this is imbalanced, this is imbalanced, this is imbalanced, and this is imbalanced. And so essentially, um, you have to pick 2 as the pivot point because this is the only way that you can write these 3 nodes as balanced. So yes, it has to be whatever the middle value is, whatever is like the Goldilocks value of these 3 has got to be the pivot point. So yeah, good question.
So when you do like a double left rotation, like for example, in your example, that's like one that goes 1, 4, 2. Yeah,
Mhm.
that one. So when you first do your single right, would 4 be the pivot point or would 2 be the pivot point?
So you're not really doing a single right here. I wouldn't say it's more of like a swap. So you're not really pivoting, you're just swapping these two. Um, so if it so it was one, what did I do? It was 1, 4, 2. You're just kind of swapping these two. And the way I like to think about it is geometrically, this kind of looks like a triangle, and geometrically, this kind of looks like a line. So you just want to go from the triangle to the line, and then from here, it's a left. So I wouldn't say necessarily either of these is a pivot point. Uh, More of like a just you swap the two. I don't know if that
Okay, thank you.
sits well in your stomach, but yeah. Um, okay. I guess let's keep blazing along. So now we got red black trees. So the reason that I cover AVL before I cover red black is that AVL is actually red black builds upon AVL. So if you don't have this concept down, uh, I would learn this first before you try to tackle red black because this concept is foundational for red black trees. So red black trees, we've got some rules. So uh, let's just define a red black tree to say that nodes are colored red or black. Uh, And this is mostly semantic, like the actual red and black value of the tree doesn't change the content of the node. You can kind of think with a red-black tree, we're trying to make like a checkerboard kind of, and so we keep track of red and black just to make sure that we're alternating in a way that is efficient and therefore the tree stays balanced. We have some rules, so the root is always black. See some other rules. We've got black height from any node is the same. And I'm going to talk about what this means in a second. And then our last rule is that, see, no to adjacent red nodes. And I'll also talk about what that means. And then also, I guess, when nodes are inserted red always. Okay, so if you follow these rules and then also a series of rotations, you're guaranteed to have a balanced tree. Just like before, an AVL tree will guarantee you that the height of the tree is order of log n. like if you do AVL rotations, it is proven that you will always have a balanced tree. Same thing with the red-black tree. It's not as good as far as like strictly balancing the tree, but it is you have to do less rotations on average, so it's preferable for that reason sometimes. So nodes are either red or black. We talked about that. Root is always black. We talked about that. Black height from any node is the same. So imagine if you've got like and I'm to save some time, I'm not gonna actually color things in. So if you've got, imagine these are the red nodes. If you've got a valid red-black tree, then you know that the black height or number of black nodes that you can count from the left and from the right will be equal at every point in the tree. So let's say we are looking at this node. Its black height is going to be, from the left, we're going to measure 1, 2. And from the right, we're going to measure 1, 2. We could also measure 1, 2 like this, right? But the black height here is going to be 2. And it's important that when you count the black height from the left or the right, you start by counting the root, and then you add 1 for every black node that you hit until the end. Technically, if you have like, if you were to say you've got like null pointers at the end of each node, null pointers are considered to be black. So if you were to count this as 1, 2, 3 black nodes, that would be a mistake. You either count both the root and all of the children, or you count this null pointer and you don't count the root. Either way, if you're looking at a structure that looks like this, you need to be able to say there are 2 black nodes. And so, for instance, if you had something like this is no longer a valid red-black tree, because as you can see, the black height on the left is now greater than the black height on the right. And then what I mean by no two adjacent red nodes, this is fine. So these two things are fine. That's okay. You're allowed to have that. What you're not allowed to have is this. By adjacent, I mean like related, like parent to child. This doesn't work. Like you couldn't have this, couldn't have that. So our red-black rotations essentially exist pretty much to just guarantee that these rules are never broken. So the rules, if you formalize them, end up giving you something like this. So number 1, the first rotation you might, or recolor you might have to do is insert root recolor to black. So if you insert all nodes as red, so we insert, say, node A and we say it's red. If we insert this node like this, in order to make it a valid red-black tree, all we have to do is recolor, say it's black, therefore the root's black, and we're all good to go. That's a simple case. If we insert a node, if we insert to a red, we insert to a black parent, again, nothing changes. We're good to go. This is fine. This is always fine, and this never causes an issue. But if we insert to a red parent, now we have to look at the uncle. So go to uncle. And so that'll give you one of two things. So either you've got a black uncle, or you've got a red uncle. So if y'all want me to talk about this more thoroughly, I think it was week 9 or whatever the last Sunday review was, I covered this pretty thoroughly, but you can kind of think of this as like case A and case B under case 3. And so if the uncle is black, you're going to balance plus recolor. And if the uncle is red, you just recolor. And I think I'm really cute. I think I'm adorable. Notice how if the uncle is black, you balance, and if the uncle is red, you recolor. So maybe that's just a little mnemonic device that'll get you out of trouble. So what does this look like? What does it mean to balance or recolor? So balancing is AVL. So think AVL because you're actually doing AVL cases. So imagine you've got the case in which you've got a black uncle. and you're inserting to a red node, a red parent. In this case, you're going to fix this by doing an AVL balance, and you're going to recolor this node and this node. So if let's label these. So let's label this 1, 2, 4, and 3. This is now going to become, we're going to AVL balance around these three. This is going to become this. So we've got this will be 3, 4, 2, and 1. And we recolored 4 and 2. So 4 was red, we make it black. 2 was see, did I do that right? It's gonna end up looking like this, I think. I'm pretty sure. Yes, we recolor 2 and 3. Actually, my bad. I'm kind of squinting my eyes as I look at this because this is going to become the case. Like in AVL, this is going to become this. And let's see, yeah. 2, 3, 4. So you always recolor the parent and grandparent once you've reached this case in AVL. And as you can see, 2 was black and became red, and 3 was red and became black. Yeah, that's correct. So that's what you do if the uncle is black. You balance and then you recolor, think AVL. And if the uncle is red, which is going to look like this. So imagine you're inserting here, you've got 2 red nodes, and you insert a new red node. If the uncle is red, then you are going to recolor the parent, the grandparent, and the uncle. So that's going to look like this. So it's going to look like that. And in the case where if this is the root, then you're going to recolor it back to black there. But in this case, let's just leave it there. So these are your rules for maintaining a red-black tree. We've got 10 minutes left, so let me quickly go through an example. Or what did I do? Did I mess up, y'all? Sorry for tripping. I'm currently tripping. I guess I deleted everything. Weird. Okay. Yeah, sorry, okay. So let's quickly go through an example. So if we've got nodes that look like this, and for the sake of brevity, I'm not going to actually, click to the red pin. I'm just going to actually do this example. So we insert 9 as red. This is case 1 where we insert as red. We have to recolor the root to black. And we're all good. Pass all the checks. All the rules are valid. We insert 7. We insert all nodes as red. This is fine. The black height is still 1 everywhere. We don't have adjacent red nodes. We're good. We're going to insert 8. So you can see we've got a problem because we've got 2 adjacent red nodes. You can think of the null pointer here being black. So now, as you can see, red node, red parent. This is case 3. We have to now think about the uncle. We've got a black uncle. So we've got to balance and then recolor. So this is going to be an AVL balance. So we have what, 9, 7, 8. We're going to do an AVL balance, which is going to give us this. And then we're going to recolor this one and this one when we get to this step. So sorry if I'm blowing through this. Red-black trees are like mad complicated. And they definitely deserve some attention. So if you're not like flying through this section, please like spend some time on your own studying this stuff because it will come up on the test. But anyway, so now it's balanced again. Let's insert 1. Now we've reached the case where red child, red parent. This is case 3. We're looking at a red uncle, so we recolor. So this was red, we're going to turn it to black. This was black, we're going to turn it to red. And this was red, we're going to turn it to black. And then as you can see, the last thing that needs to happen is just recolor the root as black. This was case 1. And then this is a valid red-black tree once again. Let's insert 2. So 2 will go here. 2 is red. As you can see, we've again reached the case where we're inserting to a red parent. We have a black uncle. So that is this AVL case. So 7, 1, 2. And for this time, I'm going to write out the color so you can actually see. And this is going to become the double right case in AVL. So here we go. And we're going to swap the color of the parent and the grandparent. So that's going to give us 2. We're going to swap its color. 1 stays red. We got 7. We're going to swap that color. And like before in a red-black tree, we're going to replace verbatim this AVL rotation. So before we had 8 black, 9 black, and then now let's add what we just decided. Should give us this. 2 is black, and then we got 1 red and 7 red. So once again, valid AVL tree. We got a black height of 2, black height of 2, no adjacent red nodes. We're all good. Let's see, let's add 3. 3 would go here, and 3 we're going to insert as red. You can see now we're looking at the case where we've got we're inserting a red node to a red parent, and we've got a red uncle. So this is case 3B, where all we do is we recolor. So we recolor the parent, we recolor the grandparent, and we recolor the uncle. And I think this fixes it, because now we've got black height of 2, black height of 2. That should be good. No adjacent red nodes. I think this is still valid. So we inserted 3. Let's insert 4. Okay, so 4 is going to be here. 4 is red. So it looks like red node, red parent, black uncle. So this is going to be the AVL case again. So we've got 7, 3, 4, red, red, black. This is going to be again a double right. So 7, 4, 3. And then we're going to change this to be 4, 3, 7. We're going to recolor the parent and the grandparent. It's going to give us this, and then let's plug that back into the tree. So we had, I'm actually going to redraw this for the sake of space. We had 8, 9, and 2. And then here we had 1 and whatever this new thing is. So 4, 3, 7 should be coming off of 2. Yeah. And so what did we decide? This was red, red, black. 1 was black. C2 is red. Yeah, and as you can see, we've got a black height of 2, black height of 2, black height of 2. This is all good. I would go watch week 9 if you're not comfortable doing this very quickly. I don't know why my iPad is tripping. But I'm gonna go ahead and call it here. Does anyone have any questions? I know that was a lot. Like I just dumped a crazy amount of information on y'all in the last 2 hours.
Is there gonna be 2, 4, 3 on the exam?
Is there gonna be this kind of stuff in the exam? Yes, there will be.
I mean, 2, 4, 3.
Yes, yeah. I think 2, 4 trees are the most accessible. So sorry I didn't cover them. But I think that concept should be y'all should be able to handle it, I think. For the 2, 4 tree, you need to know things like what is the maximum height of a 2, 4 tree? What is a 2 node? What is a 3 node? A 4 node? What do those things mean? How many children can a 2 node have? How many children can a 3 node have? So on and so forth. So that's the kind of thing you'll need to know. Sorry, I didn't have time. I mean, I would make this review 3 hours if y'all think that that's more helpful, but I don't want to force people to sit through that much content. So I don't know. It's a balancing act as always. Any more questions?
How about skip list?
Skip list? Yes, skip lists probably will be on the exam, but they're not the highlight. For lists, mostly what you need to know is like, if you were to implement a stack with a list, what is the time complexity? If you were to implement a queue with a list, or this certain operation with the list, what is the time complexity? So on and so forth. Other questions? Okay, well, thank you all for being here for the review. If y'all have like any extra questions, email me, come see me in office hours. Y'all are gonna do great. The exam is gonna be nothing.
I appreciate it, man. Thank you.
Yeah, of course, of course.
Thank you.
Mhm.